All right, this next video is going to focus on Lewis structures, how you can describe them in 3 dimensions with geometries, examine how the electrons are dispersed throughout the molecule with polarities, what a theory behind how the molecules have been described in terms of their electronic arrangement, which would be hybridization. And then another way we could characterize bonds, which are sigma and pi. What you see here on this table are Lewis dot symbols for elements that are part of the main block, groups 1, 2, 13 through 18. You will notice that these elements can have up to 8 electrons around them. They have the number of electrons that are in their valence shell, their s and p sublevels. So everybody in group 1 can only have 1 valence electron. Every element in group 2 can have up to 2. And when we go all the way down to group 18, the max they can have is 8. And that's what we are attempting to do when we are pairing ions together, or when we are sharing electrons within a molecule or an ion, is to meet every element's electrons needs so that their octet is completely filled and that they have a filled valence shell of electrons. So we can use those Lewis dot symbols for individual elements to create what we call Lewis structures. And they basically are showing us how the valence electrons are arranged around atoms in a molecule or an ion. They are not necessarily showing what they would look like in 3 dimensions, just what they are giving us a representation of what connections exist within the molecule, what types of bonds, whether they're single, double, or triple, and what electrons are not being shared. Lone electron pairs will only be assigned to an individual atom, while bonding electron pairs will be assigned between atoms. You can represent these bonding pairs with a line or a pair of dots. I've actually seen lone electrons be represented with lines too, but that gets a little crazy. The vast majority of elements on your periodic table that are going to be involved with sharing electrons, which is what we're showing you with these Lewis structures, are going to be atoms that want to have a filled valence shell of electrons. They want to have that noble gas configuration and therefore obey the octet rule, which is that there are 8 electrons surrounding that atom. There are some exceptions to that. We'll get into those shortly. But when you're drawing these Lewis structures, you need to figure out how the atoms are arranged in your molecule or ion. Typically, your least electronegative atom will go in the center. Hydrogen can never be that, and then your halogens will only rarely be in the center. We then go ahead and tally up, rather than assigning the valence electrons that are already on individual elements, we go ahead and tally up all the valence electrons that our atoms have brought to the table to be shared. And once we get that number, we start to distribute them around those elements in a molecule or an ion. One pair of electrons gets placed between each of the atoms so that the pieces making up our Lewis skeleton are connected together. And then the lone electron pairs that are just going to be assigned to a given atom start to be placed around the terminal atoms, the ones on the outside of your molecule. Keeping in mind, hydrogen will never want more than 1 pair of electrons because it only has that s sublevel available for its electrons. And with the goal that all the terminal atoms besides hydrogen will get their valence shells filled. They'll have 8 valence electrons surrounding them. If there are any additional electron pairs remaining once that has been completed, they should go on the central atom. And if for some reason that central atom does not have a full valence shell, we can share more than 1 pair of electrons between it and one of the adjacent atoms, forming either a double or sometimes even a triple bond. I said we'd come back to the exceptions, and we're going to get there right now. There are elements in the second row of the table. They're super small, and they tend to, they are fairly stable without having a full set of valence electrons. Boron's the one we commonly run into. Boron is quite happy with 6 valence electrons. Beryllium's a metal, but because it's small, it is definitely not as metallic as maybe some of the others do property-wise. It's capable of having four. Hydrogen, because of that one orbital that's available to it, will only take two electrons total, so it follows what we call the duet rule. And the one that's kind of different are the ones that can go beyond the four pairs of electrons, and that would be the elements in periods 3 or higher. They are able to do that because they have empty d orbitals, and those d orbitals can store additional electron pairs. So when we're writing these Lewis structures, our goal is to make sure that our elements have the 8 electrons, those who need them first, and then any remaining electrons would go around those atoms that can accept more than 4 pairs, the ones in period 3 or higher. So in this first example, we have POCl3. Phosphorus has 5 valence electrons, oxygen has 6, chlorine has 7. When you tally those together, accounting for the fact that there are 3 chlorines, we get 32 valence electrons. Of these 3 elements, phosphorus is the least electronegative, so the oxygen and the 3 chlorines will go around it. Again, it does not matter the location of the chlorines, it's just that they need to be connected to phosphorus. So we have used up 8 of our electrons to connect phosphorus to those atoms, and we have 24 remaining. Phosphorus has its 8 electrons, but the 3 chlorines and oxygen do not. So if we put 3 pairs of electrons or 6 lone electrons on each of those terminal atoms, we will have all of the valence electrons that the 4 atoms brought together when they wanted to form a molecule um, divided so that all atoms now have a filled octet. With NF3, nitrogen has 5 valence electrons, fluorine has 7. 3 times 7 gives me 21, and then the 5 from nitrogen would give me a total of 26. Nitrogen is less electronegative than fluorine, so it'll go in the center. We used up 6 of the 26 electrons to connect nitrogen to each of the fluorine atoms. 20 are left. We're going to use up 18 of them to take care of the lone electron pair needs of fluorine. We have 1 pair left. Nitrogen needs 1 more pair of electrons to get its full octet. And so now all atoms in this molecule are surrounded by 4 pairs of electrons. We have a stable molecule. When we run into these molecules that do not follow the octet rule, we want to make sure that we do things exactly the same, but if we end up with extra electron pairs, we need to consider if that central atom is going to be able to take those on. Here is ClF3. Chlorine has 7. Fluorine's in the same group as chlorine, so it too has 7, but we have 3 of them. So 21 plus 7 gives me 28 electrons. The fluorines are going to go around chlorine, which is less electronegative than it. I've used up 6 of my 28 electrons to connect the fluorines to chlorine. I'm going to use up another 18 to connect or to make sure that the fluorines all have full valence shells. At this point, I have used up, sorry, I'm doing my math, 24 of my 28 electrons. I have 4 remaining. So we're going to need 1 pair to go on to the chlorine in the center because it still needs a 4th pair. But because we have 1 pair remaining, that 5th pair will also be able to go on chlorine's atom. Because chlorine is in period 3 or higher, it has open d orbitals, which can accept additional pairs of electrons. With BCl3, boron's in group 13. It has 3 valence electrons. Chlorine is 7. You've got 3 of them, so together you have 24. Boron is less electronegative than chlorine, so boron will go in the center. The chlorines will go on the outside. I've used up 6 of my electrons so far. I'm going to use up 18 more to take care of chlorine, and that is all of my valence electrons. Remember, however, boron is quite content with 6 valence electrons around its central atom. So every atom that needs 8 has 8, and boron's needs are fulfilled as well. With SF6, right there you kind of know that sulfur is going to have to be your central atom. It definitely is less electronegative, and that we aren't going to be following the octet rule because there's no way that we can connect all of those fluorines to sulfur without doing that. Sulfur had 6 valence electrons. The 6 fluorines had 7. Together you have 48. We've used up 12 so far, and we're going to use up the remaining electrons to take care of the fluorine atoms to have full valence shells. Sulfur already has 2 extra pairs of electrons because of those open d orbitals. With Cl3 minus, this is one of the few times a halogen will be the central atom. There's no way around it since all you have are chlorines, but you actually have 21 electrons for the 3 chlorines, and you can't have an odd number of electrons and be a stable molecule. So this is going to be an ion, and you'll notice that next to the 3 there's a minus. That minus tells me that 1 electron has been gained, so we're going to go from 21 to 22 electrons. If it had been positive, we would have lost an electron. So we're going to connect the chlorines to one another, using up 4 of my 22 electrons, and we're going to use up 12 more of my electrons to take care of the chlorines that are terminal. So at this point, we've used up 16 of our 22 electrons. We have 6 pairs remaining. The chlorine in the center needs at least 2 pairs, but we have 1 more left after that, and the chlorine in the center is able to take that on with its open d orbitals, so therefore it would be able to have a 3rd pair of lone electrons assigned to it. You do want to make sure that you at a minimum put next to any ions their charge, so that we indicate these are not neutral molecules, that these are indeed charged ions. So that was drawing the structures, and there's no real wrong way to draw the structures as long as you don't violate the octet rule for the elements that can't violate it, that you only add additional electrons to the central atom if they're in period 3 or higher, that you don't give more than 2 electrons to hydrogen, that you always put your least electronegative in the center, electronegative atom in the center, and that you remember that boron and beryllium are not obligated to take on additional pairs of electrons, 4 and 6 respectively, 4 for beryllium, 6 for boron, and that they are not stable gaining additional electrons due to their nuclear charge. Vesper is going to describe what these molecules look like if we were going to see them in 3 dimensions, how these electron pairs are going to minimize repulsions between one another. So it allows us to predict 3-dimensional shapes. Vesper stands for valence shell electron pair repulsion. And the idea behind this is that these electron pairs, whether they are bonding or lone electron pairs, repel one another and want to minimize how close they get to one another to reduce those repulsions. Lone electron pairs, however, because they are not being shared, will be able to exert a little bit more force over the shared electrons and therefore can push them a little bit more away. The 5 base areas we will see these electrons be shared in. When you have 2 areas of electrons around the central atom, you tend to be linear in shape, 180 degrees apart from one another. Trigonal planar is what we see with 3 areas, 120 degrees apart. And once we get into 4, 5, and 6, we're really definitely looking at things in 3 dimensions. With 4, it's a tetrahedral, as opposed to if we looked at it just in 2 dimensions, we can get a little bit more space if the molecule is examined in 3 dimensions, 109.5 degrees. Trigonal bipyramidal, you have a pyramid on the top and on the bottom, that trigonal base there in the middle, and those atoms are 120 degrees apart, while the peaks of the pyramid are able to be 90 degrees apart from the trigonal middle, and they're able to be 180 degrees apart from one another. Octahedral is going to follow the same type of logic, but rather than having a triangle in the middle, it's going to have a square in the middle. So once you have areas of electrons around your central atom, and if they're all being shared equally, all the atoms that are bonded to that central atom are similar in electronegativity. There's no one element pulling on the electrons more than the other. You just get that parent geometry. However, when one of those bonds gets replaced with a lone electron pair, you'll start to see some distortion in your geometry. It will no longer be that parent shape. In this case here, once you've lost one of those bonds, you now form what we call a trigonal pyramidal. And the bond angle gets reduced slightly because a lone electron pair, again, is trying to take up more space. and minimize those repulsions. With the bent molecule, you have two areas of lone electrons that are trying to minimize interacting with one another as well as with the hydrogen atoms, and they push the hydrogen atoms even closer together at a 104.5-degree angle. With 5 and 6, similar logic occurs. You start with your base shape as long as they're all bonded. When you start to replace bonds with lone electron pairs, your geometry is going to change. With the 5 electron pairs, the electron pairs get removed from the triangle part first. So one removal to a lone electron pair becomes seesaw, a second one becomes T-shaped, and the third one actually is able to become linear because the electron pairs are all in that triangle plane and the rest of the atoms are 180 degrees apart. With octahedral, once the first one has been replaced, you are going to go to square pyramidal. And then once you replace the second one, now you are going to have a square planar. So if I wanted to describe the geometry of these molecules, I would want to take a look at how many areas of electrons will be around the central atom. Are they being shared or are they not being shared? So with POCl3, we see that there are 4 areas of electrons around that central atom. They're all being shared. And so when you have those 4 areas, that would be classified as tetrahedral. With NF3, we have 3 shared areas around the central atom and 1 lone electron pair. That 1 lone electron pair is going to distort our geometry a little. And so instead of being tetrahedral, now we're going to be trigonal pyramidal. With ClF3, we have 5 areas of electrons around the central atom. Lone electron pairs count as a separate area of electrons. Multiple bonds do not. If you have a double or a triple bond, they only count as one area. But in this particular one, we have 3 bonds and 2 lone electron pairs. So we know this is coming from that trigonal bipyramidal shape. And when you lose 2 of those bonds and replace them with lone electron pairs, you are now T-shaped. With BCl3, we have 3 areas of electrons around our central atom. We have no lone electron pairs, so all of these atoms are able to separate from one another, the bonds, pretty evenly, and you would have a trigonal planar shape. With SF6, we have 6 bonds around the central atom, so they are all going to spread out as uniformly as they can, and you have your parent octahedral geometry. With Cl3-, this is one that has the 5 areas of electrons around the central atom because you have the 3 lone electron pairs and the 2 bonds. And when you replace those 3 bonds that make up the trigonal part of trigonal bipyramidal with lone electron pairs, you actually are going to have a linear shape. So I've talked about Lewis structures. I've talked about 2 dimensions. I've talked about 3 dimensions with geometry. Now we're going to talk about polarity. And you can have polar bonds. Polar bonds are going to occur between any pair of atoms that don't share electrons in exactly the same way or have similar electronegativity values assigned to them. However, within a molecule, if those electrons are being shattered in the same manner, you're going to have symmetry. Dipoles or polar molecules are going to have asymmetry. They're going to have an area where there are more electrons compared to other areas of the molecule. So you definitely have to consider it looking at the molecule in 3 dimensions as opposed to 2. There are various actors that can play a role in having an impact on these dipoles forming. Different atoms with different electronegativity needs are one. Another would be single electron pairs or even sometimes 2 lone electron pairs that are going to distort your geometry. There's not going to be a way to cancel them out in all 3 dimensions. And then also different types of bonds that cannot be distributed, such as double or triple bonds. So here in this particular model, most of the time tetrahedral is going to be nonpolar. But because you have oxygen, which is different electronegativity-wise than the three chlorine atoms, you are going to have asymmetry occur, and this would be considered to have a dipole moment, be a polar molecule. With NF3, you have three bonds between N to fluorine, but you have a single lone electron pair on that central atom. And that's the one we're always focused on when we look at polarity. Same with geometry. What does everything look like in regards to that central atom? Anytime you have a single lone electron pair on the central atom, you are guaranteed to be polar. With ClO3 minus, you will notice here you have the three areas of electrons between Cl and each of the O's, and you also have another lone electron pair. Lone electron pairs by definition are polar. With ClF3, we have the three bonds between the fluorines and chlorine. Remember, one of them is in that triangle, the other two are 180 degrees apart, so you're not going to have symmetry there. You're also not going to have symmetry with the two lone electron pairs, and so that's going to allow this molecule to be polar. BCl3, if we look at it here as I've drawn it in 2 dimensions, looks like it's going to be polar. But remember that when you have three shared areas of electrons around a central atom, they actually can get 120 degrees apart and form a trigonal shape. And so because there are no lone electron pairs, all the atoms bonded to boron are the same, and there's no multiple bonds, this is actually a very nonpolar molecule. There is symmetry across the board in this molecule. With SF6, we see a similar process. You've got the fluorine atoms coming up and down on the y-axis, and then the other 4 fluorine atoms are in that square plane in the center. There's symmetry looking at it from the y-axis and x-axis, so this would be nonpolar. And Cl3 minus, and there's for square pyramidal for octahedral with 4 bonds and 2 lone electron pairs are the 2 instances with lone electron pairs you kind of got to keep your eye on with polarity. The chlorine atoms are 180 degrees apart from the central chlorine atom. So no matter whether we're looking at it on the x-axis or y-axis, there's symmetry there. With the lone electron pairs, remember that they are 120 degrees apart from one another. So there's actually symmetry among those lone electron pairs as well. And because there's symmetry among the lone electron pairs and among the bonds, in this particular example, you actually can have lone electron pairs that are going to have that particular ion is going to be nonpolar. Again, this particular geometry where you have the 2 bonds and the 3 lone electron pairs within trigonal bipyramidal, and then within octahedral, 4 bonded areas and 2 lone electron pairs. Those are the 2 you kind of have to caution yourself with. So valence bond theory is basically attempting to come up with a way to explain how these shapes have come to be. And it's thought that perhaps mixing orbitals together where these valence electrons are located can form hybrid orbitals. And they will mix based on the numbers of areas of electrons around that central atom. You need some overlap to be able to have electrons in the same orbital, but you don't want a ton of overlap because then you're going to have repulsion. You also don't want them so far separated that there is no attraction for one another. So you have optimal lengths at which these orbitals can be around one another. With sp3 hybridization, if we take a single s orbital and 3 p orbitals and those are mixed together, you can form that tetrahedral shape, and the electron pairs, those orbitals, can get about 109.5 degrees from one another. With sp2 hybridization, we're looking at a molecule that has 3 areas of electrons around its central atom. So it would need 3 orbitals, 1s and 2p, and they're able to form that triangle shape, the one that's 120 degrees apart. With sp hybridization, you would have 2 areas of electrons around the central atom, and so you would blend 1s and 1p orbital together, and you're able to get the electron pairs 180 degrees apart from one another. When we start to run into those elements in period 3 or higher, that's when we start to add on additional orbitals. Here with sp3d hybridization, by taking an additional d orbital and adding it to the 3p and 1s orbitals, we're able to form that trigonal bipyramidal shape. And then finally, when we repeat what we just did but add another d orbital in, we can form an octahedral-like geometry. And so all of these hybridizations are based solely on the numbers of areas of electrons around the central atom. How many bonds do you have? I don't care what type of bond it is. How many lone electron pairs? Add those together. Your hybridization should match for that number. So we're going back to our examples again with POCl3. You have 4 areas of electrons around the central atom, so we need 4 orbitals, 1s and 3p, sp3. In F3, you have 3 bonded areas, 1 lone electron pair, so 4 areas total. That would be sp3. As would ClO3- because it has the 3 O bonds and the 1 lone electron pair. When we get to ClF3, now we have 5 areas of electrons, 3 with the bonds, 2 with the lone electron pairs. So we would need to add in a d orbital, sp3d. With BCl3, you only have 3 areas of electrons around the central atom, so you would need an s and 2 p's, sp2. With SF6, we have 6 areas of electrons around the central atom, so we're going to need the S, the 3 P's, and we're going to need 2 D's this time, sp3d2. And then finally with Cl3-, you have 2 bonds and 3 lone electron pairs. That gives you 5 areas total, so you would need 1 S, 3 P's, and 1 D, sp3d. So the last piece we're going to talk about in this part of the video is bond sharing. And this is just another way to describe those bonds that are present in a molecule and more the physical location of those bonds. Bonds, electron pairs are thought to form between those atoms in that space where we draw the line or the pair of dots. And when they're in the plane along that bond, that's what we call a sigma bond. And so every type of bond, whether it's a single, double, or triple, is going to have a sigma bond. That is the covalent bond that forms between the 2 atoms directly. When you have multiple electron pairs being shared, there's still going to be a little bit of repulsion, so they actually are going to kind of overlap and form above and below that bond's axis. And so when you have a double bond, you will have 1 pi bond and 1 sigma bond, the one that's in the plane and the one that's above or below it. Whereas with a triple bond, you would have 2 pi bonds because you'll have a pair of electrons above, a pair of electrons below, and then the pair that are directly within the axis. So if I take carbon monoxide, carbon has 4 electrons, oxygen has 6. I want to arrange those 10 electrons around carbon and oxygen. I would get a triple bond for C to O. So this particular molecule, again, it's got to have one of those pairs within the plane where carbon and oxygen are. The other 2 are above and below it, so 1 sigma and 2 pi. With C2H4, the carbons are going to be bonded together. The hydrogens are going to be split between the 2 carbons. So you're going to need a multiple bond to keep the carbons bonded to one another and fulfill their octet needs. So you actually have 4 single bonds and 1 double bond in this molecule. So you will have a total of 5 sigma bonds because every bond has a sigma bond. And because you had 1 multiple bond that was a double bond, you'll have 1 pi bond. And we will save formal charge for our next video.